Welcome all. This is lecture number 3 on beta and gamma function. Dirichlet's integral. In this lecture, we will discuss Dirichlet's integral and the extension of Dirichlet's integral, that is Liouville's integral theorem. So first, what is Dirichlet's integral? This integral is useful to evaluate the double and triple integrals by expressing in terms of beta and gamma functions. The following formulas are used to evaluating the multiple integral. The first statement, if let capital R be the region in xy plane and it is bounded by x is greater than equals to 0, y is greater than 0 and x plus y is less than equals to h. Then double integral are x raised to power L minus 1, y raised to power m minus 1, dx dy is equals to gamma L gamma m upon gamma L plus m plus 1 h raised to power L plus m. It means that if there is double integration in this particular form and limits are in this particular form, or if we convert the limits in this particular form, then we can write this double integral directly in the gamma function form. Statement 2, let V be the region where x is greater than equals to 0, y is greater than equals to 0, z is greater than equals to 0 and x plus y plus z is less than equals to h. Then triple integral V x raised to power L minus 1, y raised to power m minus 1, z raised to power n minus 1 dx dy dz is equals to gamma L gamma m gamma n upon gamma L plus m plus n plus 1 h raised to power L plus m plus n. So similarly, if we convert limits for a problem or for the volume integral basically in this particular form, then we can directly solve the triple integral with the help of gamma function. Note, let V be the region where x is greater than equals to 0, y is greater than equals to 0, z is greater than equals to 0 and x plus y plus z is less than equals to 1, that is h is equals to 1. Then triple integral V x raised to power L minus 1, y raised to power m minus 1, z raised to power n minus 1 dx dy dz is equals to gamma L gamma m gamma n upon gamma L plus m plus n plus 1. It means when we put h equals to 1, then h raised to power L plus m plus n will become 1. So only this particular formula remains. Now Liouville's extension of Dirichlet's integral. If the variable x, y, z are all positive such that x plus y plus z is greater than h1 and less than h2, then triple integral f x y x plus y plus z x raised to power L minus 1, y raised to power m minus 1, z raised to power n minus 1 dx dy dz is equals to gamma L gamma m gamma n upon gamma L plus m plus n integral this h1 to h2 means lower limit to upper limit fu and u raised to power L plus m plus n minus 1 du, and this u is this particular x plus y plus z or this particular x plus y plus z. Means if it will be x square plus y square plus z square and it is also the x square plus y square plus z square, then we can replace u by x plus y plus z, or we have to convert this limit in term of the function. Now the example 1, find the volume of the tetrahedron bounded by the planes x equals to 0, y equals to 0, z equals to 0 and x plus y plus z equals to a. So we know that the volume of a solid is triple integral V dx dy dz. This is the standard formula to find the volume of a solid. So first we have to find the limits and we can write it in the form of the Dirichlet's integral, because there is not the function. So we have to formulate it into the Dirichlet's form, that is we can write x raised to power 1 minus 1, y raised to power 1 minus 1, z raised to power 1 minus 1. So from Dirichlet's integral for the limit, since there is x equals to 0, y equals to 0 and z equals to 0 and x plus y plus z equals to a. So this x plus y plus z is bounded by 0 to a. So the limit lies between 0 to a, and this is of the form Dirichlet's integral because there is not the function initially. If there will be function, then we have to apply Liouville's extension, and if there is not a function, then we can apply Dirichlet's integral. So from here, L is 1, M is 1, N is 1. So gamma 1, gamma 1, gamma 1 upon gamma 1 plus 1 plus 1 plus 1 into a is at the place of h, so a raised to power L plus M plus N, that is 1 plus 1 plus 1, or gamma 1 is 1 and this is gamma 4. So a cube upon gamma 4, and gamma 4 can be replaced by factorial 3 and factorial 3 will be 6. So the volume of this particular integral is a cube by 6. Now see, we solved this particular problem in a very easy manner in 2-3 steps only. And if we have to solve this by the normal or traditional method, then we have to write the limit x equals to 0 to a, y equals to 0 to 1 minus a minus x, and z equals to 0 to a minus x minus y, and then integrate it. So this particular Dirichlet's integral and Liouville's extension both are the easiest method to solve the multiple integrals. So example 2, the plane x upon a, y upon b plus z upon c equals to 1 meets the axis in a, b and c. Apply Dirichlet's theorem to find the volume of the tetrahedron. So to solve it, volume again triple integral v dx dy dz. Now this plane is in the form of x upon a plus y upon b plus z upon c equals to 1, but we have to make it in term of x plus y plus z. So for this we can put x upon a equals to u, y upon b equals to v, and z upon c equals to w. So from here x is equals to au, y is equals to bv, and z equals to cw. And this x upon a plus y upon b plus z upon c is converted into u plus v plus w equals to 1. So dx will be a du, y dy equals to b dv, and dz equals to c dw. So on replacing all these in this particular volume, so triple integral dx is replaced by a du, dy is replaced by b dv, and dz is replaced by c dw. So a, b, c are the constant, so take them outside the integral, and there is no function, so we have to write in term of Dirichlet's form, that is u raised to power 1 minus 1, v raised to power 1 minus 1, w raised to power 1 minus 1. So we can apply here Dirichlet's integral for u plus v plus w lie between 0 to 1, because in this particular problem it is said that this plane meets the axis in a, b and c. So the initial value for the each point is 0. That's why u plus v plus w lie between 0 to 1. So volume is equals to a, b, c, gamma 1, gamma 1, gamma 1 upon gamma 1 plus 1 plus 1 plus 1, and since h is equals to 1, so there is no h. So gamma 1 is 1 and this is gamma 4. So ABC upon factorial 3, or we can say it is ABC upon 6. So this is the volume of for this particular plane. Example 3. Apply the Dirichlet's theorem to evaluate the integral triple integral v x y z dx dy dz taken throughout the ellipsoid x square upon a square plus y square upon b square plus z square upon c square is less than equals to 1. So we have to solve this particular integral for this ellipsoid. So first we have to simplify the equation of the ellipsoid to apply the Dirichlet's theorem. So for this we can put x square upon a square is equals to u, y square upon b square is equals to v, and z square upon c square equals to w. So from here this equation is converted into u plus v plus w is less than equals to 1. So now the condition is converted into the appropriate form. Now we have to change this integral in term of uv and w. So for this we have to find the value of x, y, z and dx, dy, dz. So we can rewrite it as x square is equals to a square u, y square is equals to b square v, and z square is equals to c square w. So on differentiating we get 2x dx equals to 2a square du, or x dx is equals to a square by 2 du. Similarly y dy is equals to b square by 2 dv, and z dz is equals to c square by 2 dw. So on replacing this x dx, y dy and z dz in the integral, because x dx combined, y dy combined and z dz combined, so we can rewrite this integral in term of a square by 2 du, b square by 2 dv and c square by 2 dw. So a square, b square, c square upon 2 into 2 into 2 can take outside the integration. Only integral, triple integral du, dv, dw remains, and we have to convert it into the Dirichlet's form. So we can write here u raised to power 1 minus 1, v raised to power 1 minus 1, w raised to power 1 minus 1. So now we can apply Dirichlet's formula for u plus v plus w lie between 0 to 1. So a square, b square, c square upon 8, this will be 8, and gamma 1, gamma 1, gamma 1 upon gamma 1 plus 1 plus 1 plus 1, and h is 1. So there is no need to write h, or this will be gamma 1 will be 1 and it is gamma 4. So a square, b square, c square upon 8 into 1 upon 3 factorial, and 3 factorial is 6 and 8 6 are 48. So a square, b square, c square upon 48 is the required value of the given integral. Example 4. Show that triple integral v dx dy dz upon x plus y plus z plus 1 whole cube is equals to 1 by 2 log 2 minus 5 by 16. The integral being taken throughout the volume bounded by the planes x equals to 0, y equals to 0, z equals to 0 and x plus y plus z equals to 1. So since see there is function in the problem, so we can apply Liouville's extension here. So from Liouville's extension theorem, for x plus y plus z lie between 0 to 1, we can write these planes in this particular form. So from here x plus y plus z is the condition. So we can replace this x plus y plus z by u. So applying the Liouville's extension, or rewriting this first in term of Liouville's extension, and for the Liouville's extension we have to introduce x raised to power 1 minus 1, y raised to power 1 minus 1, z raised to power 1 minus 1 here, because it required x raised to power l minus 1, y raised to power m minus 1, z raised to power n minus 1. So applying the Liouville's extension, we get gamma 1, gamma 1, gamma 1 upon gamma 1 plus 1 plus 1. Integral lower limit to upper limit, that is 0 to 1, fu means function is this x plus y plus z plus 1, and x plus y plus z is converted to u. So 1 upon u plus 1 cube into u raised to power l plus m plus n minus 1, and the value of lmn is 1. So 1 plus 1 plus 1 minus 1 du, or gamma 1 will be 1 and this is gamma 3, and gamma 3 is the 2 factorial and 2 factorial is 2. So it is 1 by 2 integral 0 to 1, this is u square upon u plus 1 cube du. Now we have to solve this integral u square upon u plus 1 whole cube du. So how to solve? We cannot solve it directly, so we can apply partial fraction to solve it. And how to solve by the partial fraction? We can write it in the form of a upon u plus 1 b upon u plus 1 square and c upon u plus 1 cube, and then simplify and get the value of a, b and c. And after solving, we can rewrite it in the form of 1 upon u plus 1 minus 2 into 1 upon u plus 1 square plus 1 upon u plus 1 cube du. Now we can integrate it directly, because 1 upon u plus 1, the integral of 1 upon u plus 1 is log u plus 1, and it this and this both function can be taken into the numerator, that is u plus 1 minus 2 and u plus 1 power minus 3. So the integral of u plus 1 minus 2 power minus 2 is u plus 1 power minus 1 upon minus 1, and the integral of u plus 1 power minus 3 is u plus 1 power minus 2 upon minus 2 under the limit 0 to 1. So this. Now apply the limits. When we apply u equals to 1, then log 1 plus 1 is log 2 minus log 0 plus 1 is log 1 and log 1 is 0. Same as 2 upon 1 plus 1, that is 2, and minus 2 upon 1, it means 2, and minus 1 upon twice 1 plus 1 2, 2 cube 2 square, and minus is already there, so it will be plus 1 upon 2 into 1 square. So log 1 is 0, so only log 2 remains, and from here this is 1 minus 2, that is minus 1, and it is 1 by 8 and it is 1 by 2. So on simplifying, 1 by 2 log 2 minus 1 by 8 plus 1 by 2, and on simplifying it, it will be minus 5 by 8, or when we multiply by 1 by 2 to the entire bracket, it will convert it into 1 by 2 log 2 minus 5 by 16, which is the required proof. So hope you understand this Liouville's extension problem. Example 5. Evaluate triple integral v x square yz dx dy dz throughout the volume bounded by the planes x equals to 0, y equals to 0, z equals to 0, and x upon a plus y upon b plus z upon c equals to 1. So from here, first we have to change this equation in the appropriate form. So for this, we can let x upon a equals to u, y upon b equals to v, and z upon c equals to w, so that this is converted into u plus v plus w equals to 1. So we have to find the value of x, y, z and dx or dy, dz. So we can rewrite this in term of x equals to au, y equals to bv, and z equals to cw, so that dx can be written in term of a du, dy is b dv, and dz is c dw. So on replacing the value of x, y, z, dx or dy, dz in this and letting this integral as I, we can rewrite it in the form of au whole square into bb into cw into a du, b dv, and c dw. Now from here a square bc and a bc, so it is a cube b square c square is the constant, so we can take it outside the integral, and u square v w remains. So this is a cube b square c square is equal into triple integral v u square v w du dv dw. Now this integral is in appropriate form because the limits are is also in the appropriate form. So we can rewrite this u square v w in term of x raised to power l minus 1, y raised to power n minus m minus 1, z raised to power n minus 1. So we can rewrite it in term of u raised to power 3 minus 1, v raised to power 2 minus 1, w raised to power 2 minus 1. So now it is in the appropriate form. So we can apply Dirichlet's integral for u plus v plus w lie between 0 to 1. So it is I is equals to a cube b square c square gamma 3 gamma 2 upon gamma 3 plus 2 plus 2 plus 1. So gamma 3 can be written in term of 2 factorial. This 2 gamma 2 is written in the form of 1 factorial, and this gamma 2 is also can be written in the 1 factorial, and it is 3 to 5 to 7 1 8. So it is gamma 8. So we can write gamma 8 in term of 7 factorial. So now open the factorial notation. So 2 factorial is 2 and 7 factorial can be opened as 7 into 6 into 5 into 4 into 3 into 2 into 1, and on simplification we get it is a cube b square c square upon 2520. So it is the required value of this particular integral. So moving on to the next example. Example 6. Evaluate triple integral v log x plus y plus z dx dy dz. The integral extended over all positive and 0 values of x, y, z subject to condition x plus y plus z is less than 1. So it contains all conditions. The initial values, initial limits are zeros, overall positive and 0 values of x, y and z. So from here x is greater than 0, y is greater than equals to 0 and z is greater than equals to 0. And the another one is x plus y plus z is less than 1. So the initial limits are x plus y plus z lie between 0 to 1. And the integral contains function. So in this particular case we can apply Liouville's extension. So from Liouville's extension theorem, for x plus y plus z lie between 0 to 1, we can write this integral in terms of integral v log x plus y plus z into x raised to power 1 minus 1, y raised to power 1 minus 1, z raised to power 1 minus 1, dx dy dz. Or now x plus y plus z can be written in the form of u, and this from here gamma 1 gamma 1 gamma 1 upon gamma 1 plus 1 plus 1 integral lower limit to upper limit, that is 0 to 1, log u into u raised to power L plus m plus n minus 1, that is 1 plus 1 plus 1 minus 1 du. So it is u square. So gamma 1 is always 1 and it is gamma 3, which can be written in the form of 2 factorial, and 2 factorial is 2. So we can write it as 1 by 2 integral 0 to 1 u square log u du. So now there are the product of the two functions, so we can apply eyelet, and after applying the eyelet we can solve this particular integral. From the eyelet, this log u taken as first and u square taken as second. So log u as it is, integral of u square is u cube by 3 minus differentiation of log u is 1 upon u, and integral of u cube upon u square is u cube upon 3 whole integral. So 1 upon u into u cube upon 3 will convert it into u square by 3, and so 1 by 3 is outside. So integral again, integral of u square is u cube by 3. So this expression exists under the limit 0 to 1. So applying, when we apply the limits, when we put u equals to 1, then it is 1 by 3 log 1. Log 1 is 0. So only minus 1 by 3 into 1 by 3, and when we put 0, then this entire function and this entire function will be 0. So only minus 1 by 3 into 1 by 3, that is minus 1 by 9 remains. So it is 1 by 2 into minus 1 by 3 into 1 by 3, or it is minus 1 by 18. So this is the required solution of this particular triple integral. So hope you understand this entire content of the Dirichlet's extension and the Dirichlet's theorem and the Liouville's theorem, extension theorem. So this is the end of this particular topic, beta and gamma function. Hope you all enjoyed this particular topic in the series of beta and gamma function in the 3 lectures, lecture 1, 2 and 3. We will meet in the next lecture with a new topic. Thank you.